Hello, welcome to Jedi lesson video 6 we're using week 4A material from Wiley Plus, and we're going to look at the first problem. So I'm going to go over the right-hand rule because it's something that we need for this problem, but first let me read the problem and then we're going to define a few of the variables. The drawings show 3 situations in which a positively charged particle is moving through a uniform magnetic field B with a velocity v. For each situation, what is the direction of the magnetic force F exerted on the particle? Alright, so we're trying to find the direction of the magnetic force F using the information that we're given from these 3 images here. So the first thing I want to do is define some of our variables. So when we're understanding magnetic forces, we need to know velocity, which is usually given by v. And so this is the rate and direction when the charged particle is moving through space. And the SI units for velocity are meters per second. Then we have the magnetic field, also known as a B field, which is represented by that. And that's a vector field that describes the magnetic influence on moving electric charges. And then the SI unit for the B field is Tesla, which is a capital T. And then the last thing I want to define is the magnetic force, which we're trying to find here. And the definition for that is a deflecting force that's exerted on a moving charged particle by a magnetic field. And we measure magnetic force with the SI unit in newtons, which is a capital N. Alright, so now that we have that defined, bear with me because I'm going to try to demonstrate the right-hand rule in a drawing, since I'm not able to show my right hand right now. But let's start with A first. So we have this first drawing, and we have our, we have our y-axis first, and this is going to be our x-axis. Okay. It's positive y, positive x, and negative x. Alright, so we know that we have this charged particle here, and it has a velocity. The velocity is pointing down, and then the B force is pointing out towards us, right? So it's positive z. Okay, so given this, I'm going to draw my hand, for example. So if we're going to use the right-hand rule, I'm going to, okay, I'm going to point my hand downwards, but since I'm using my right hand, when I'm facing this, it's going to be flopped, so I'm going to draw my thumb this way. Thumb, index finger, and okay, so my hand is pointing down in the direction of the velocity, and then I'm gonna curl my fingers. So if I'm pointing down, I'm gonna curl my fingers inwards, which would go this way. So I'm curling all my fingers upwards. So now it's gonna look like this. All my fingers are curled inwards, okay? And then my thumb is pointing this way, and that's the negative x direction. So, making sure I did this right. I guess these are technically my knuckles here. My fingers are like in the back. Anyways, so my thumb is pointing in the negative x direction. So then I know that the direction of the magnetic force is going to be negative x for this. Okay? So for A we have negative x. Now let's go to B. We have the same thing. We're drawing our axes. Okay? And then here it's slightly different because our velocity is going upwards here. We have our B force going out this way. And I'm going to draw my hands similarly. So this is going to be the right hand rule. My hand is pointing up this time because it's going in the direction of the velocity. Ooh. Index finger, middle finger, ring finger, pinky. Okay? So it's pointing up, and then my hands are going to curl. Okay? And now they're curled, and my thumb is still pointing this way, and that is in the negative x direction. So then we know that for this situation, the direction of the magnetic field is also negative x. And then lastly, we have C, which is also quite unique. I'm about to rewrite this here. Okay. So C is different than the last two because our velocity and our B field are pointing, they're parallel to each other. So because of this, we know that since velocity is pointing to the positive x direction, and so is the B field, then when the particle moves completely parallel to a magnetic field, then the angle between them is going to be 0 degrees. So because the angle between them is 0 degrees, then we know that the force is also 0. Okay, so then this leaves us with our answer being negative x, and force being 0. So if we go over to our chart here, we can see that D is our answer because we have matching results. And let's see if that's correct. And that checks out. Right, so on to our next problem, which is problem number 2 in this set. It states the drawing shows 4 situations in which positively charged particle is moving with a velocity v through a magnetic field b. In each case, a magnetic field is directed out of the screen towards you. Okay, this is good to know. And the velocity is directed to the right. In only one of these drawings is a magnetic force F physically reasonable. Which one is it? All right, so let's go ahead and imagine this. So we have our plane here, all right, and this is, we have our positive y, x, and positive x, okay? And we have a positively charged particle. All right, so we're going to be using the right-hand rule with a velocity v through magnetic field b. The magnetic field is directed out of the screen towards you, and the velocity is directed to the right. Okay, let's take that into account. So velocity is directed to the right. Okay, and if we use the right-hand rule, which we went over in the previous problem, let's go ahead and say that our hand is going to the right, right? Here's our hand. Oy. Okay, just pretend it's our hand. And then the velocity is directed to the right. Oh, and the magnetic field is directed out of the screen towards you, okay, which we can see here. It's out of the screen towards us. In one of these drawings, magnetic force F is physically reasonable. All right, so we have our fingers pointing straight to the velocity, which is this way, and then we're going to curl the fingers in the direction to the magnetic field, which is out of the screen towards us. Okay, so if we curl our fingers this way, out of the screen towards us, then our thumb is going to be pointed down. Okay, so that means that the force is F. Okay, that hand wasn't that great. So we have our hand pointing this way, and we're going to curl our fingers, and then once we curl our fingers, they're going to curl, wait, hold on, I'm trying to model it in person as well. Okay, so they're going to be like this, right? And our thumb is going to be down. Okay, perfect. That's a better drawing. So our thumb points down, so then we know that the force is going to be directed downwards. And if we look at these 4 images given to us, which one of these matches our drawing here? It's this one, number 1. So our answer should be number 1. Oh, and I should probably define one more thing. The electric charge is known as Q, and this basically shows, oh, in this problem, this is positive, and the SI unit for electric charge is coulombs, which is represented by C. And then the other variables that were needed in this equation, or good to know, I guess, in this question to define, I've defined up here, these ones. Okay, so we're going to keep going through those, and let's make sure we check it. Perfect.